This is referred to as Dalton's law of partial pressures. Dalton's law of partial pressure states in a mixture of different gases, the total pressure is the sum of the partial pressures of individual components. Now this is expressed mathematically. Dalton's law is expressed mathematically, and it's in terms of the total pressure. Total pressure being the sum of the partial pressures. It shows up like this. P total is equal to the sum, sigma, sum of all the individual pressures from I equals 1 to N. Yeah. Which means, it simply means pressure 1 plus pressure 2 plus on plus up to nth pressure equals the total pressure. So we simply say PT is equal to the sum of the individual values, which simply is 44 plus 175 plus 88 plus 25. Everything will factor 2 millimeters. Simply enough, 332 millimeters of mercury. These millimeters refer to a hygrometer gauge, where it's measured in height of mercury above standard plane, well, whatever. If you divide that by 760, you can go to atmospheres. Caution, the answer choices may be mixed in terms of millimeters and atmospheres. So if you work your problem out and you don't see 332 or whatever, convert it to atmospheres, and it'll most likely be in that dimension. This next topic is widely used in a number of sections in the future, and it's referred to as mole fraction. In a mixture of gases, the components are chemical compounds. And if we know their partial pressures, we can determine what is called a mole fraction. Well, what is a mole fraction? It is a percentage without multiplying by 100. It's part per 100, but you don't multiply by 100. For example, if you have given a mix of gases, the moles of CO2 equal 0.0234 mole, and the moles of SO2, for example, are equal to 0.1009 mole. What's the mole fraction of each of these components in the mixture? So then, well, that's not a question, that's a statement. So it's add them and add them to get the total. It's the part over total times 100. So the mole fraction of an individual component is equal to the moles of the individual component divided by the sum of the individual moles from I equal 1 to n, just like we did in the partial pressures, which simply put is N1 plus N2 plus ... all the way up to however many mole fractions. We only have 2 here. And if you're interested in specific one, first one, second one, third one, N over the total, and that's your mole fraction. You don't multiply it times 100. Okay, mole fraction percent. Some people will do that, which is okay. I mean, it's really your world when you're working with it. Okay, for the case here, we have moles of CO2 and SO2 in a container. So the sum of the moles is simply 0.0234 plus 0.1009 mole. And they now want to calculate the mole fraction of CO2. Okay, so it is 0.0234 divided by 0.1243. You will have no units because moles are on the top and moles are in the bottom in this ratio. Okay, so there's your mole fraction for CO2, and your mole fraction for SO2 is computed the same way, 0.1009 mole divided by the total, 0.1243 mole. Individual mole fractions. Now, one way to check this work here is that the sum of all your mole fractions always equals 1. It's like all your percentages. Part of a total, you add them up and they all give you 100%. Well, since we're not multiplying by 100, it all adds up to 1. So if we 0.1883 for the CO2 plus 0.8117, we add that up and we get 1.000. Okay, so that confirms the accuracy of your calculation, right? If you are given a mixture of gases, each partial pressure can be defined by the ideal gas law. Also, the total pressure can be defined by the ideal gas law. That is, of course, moles of I over the sum of all your Ni moles. You know, supposed to, PV equals nRT. Solve this for N and substitute it into this expression, as that were 1 N sub I and 2 in total. So you have, well, let's do it this way. A N sub I, the top of this expression, is equal to PV over RT. And B in total, NT, is equal to, well, this pressure of the individual one, and this is P total V over RT, like that. So this is your total sum here. B is for your total sum, I is for the numerator, and so we can set this up as a PV over RT for the individual. And that's the individual partial pressure right there, divided by P total V over RT. Like that. Okay, so the top is the individual, because I took that out of the ideal gas law and I put it up here. And then the bottom I assumed to be the total moles, so adding the moles all together, and I put it in the denominator. Well, volume, R, and T are constants. So they cancel out. I'll do that. P individual volume over RT times RT over P total times RT, P, well, RT over PV. Okay. The mixture is in one container. Okay, so when we talk about the mixture of two gases, however many they are, we're talking about the mixture in the same volume. So they all have the same volume. Well, of course, they're all going to be in the same container with the same temperature. So the temperature cancels out, volume cancels out, and we know this is a constant, that cancels out. So we have the mole fraction of any individual component is also equal to the partial pressure of a component divided by the total pressure that you're given in a mix.